Now that we have a little bit of background on electric fields and their quantity and electric forces, we're going to go through the steps to actually construct an electric field map. We're going to do it for a positive and a negative charge. I've drawn them on my graph paper, and in order to draw the electric field map, I'm going to need to know some electric field vectors around the space. And my electric field map is representing a separation that is on the order of the size of an atom. So this distance here will be representing 1 times 10 to the negative 10th meters. And if I get my ruler out, let's just see how far distance that is in centimeters. Looks like 11.75 there. So this will be just representing 11.75 centimeters. That's what I'm going to use for my distance scale for this map. So the first thing I'm going to do is select some points around here for which to calculate the electric field. And if I use symmetry, I can save myself a lot of work. So what I did is I selected points that are 3 blocks away from the charge. And then I also selected a point, even though it's 3.5 blocks, directly in the center of the positive and the negative charge. So the first thing I'm going to do is organize myself so that I can reduce the number of calculations that I do. And I've laid this out on a spreadsheet on Excel, but I'm going to show you writing out the calculations by hand, how to do it for the first line, because after that you can simply put the numbers in the spreadsheet itself and then copy down the formula. But it's good to know what's going on for the first line. So our positive centimeters, kind of used abbreviations here so that it fits across the screen. That means the distance that's in the electric field formula measured on the graph paper in centimeters. So let me look at my first line. Let me get my ruler out again. And point A is right here in the center, so that's where I'm going to start. Whoops, doesn't need to rotate. Point A is in the center, and it is 6 centimeters on my ruler. I'm looking at this 6 right here from the positive charge. And let's see where it is from the negative charge. It's about 6 centimeters from the negative charge as well. Okay, so let me go back to my spreadsheet, and let me put those numbers in the spreadsheet. Okay, now to scale that to a meters representing the size of an atom, I'm going to say 1 times 10 to the negative 10th meters represents, oops, a little crooked there, 11.75 centimeters. How many centimeters, or how many meters, will be represented by 6 centimeters? So by point A away from the charge. To solve this, I'm going to multiply both sides by 6 so I can cross it out here. So I get 1 times 10 to the negative 10th meters times 6 centimeters divided by 11.75 centimeters. My centimeters cross out, and I have meters left for my unit, and the answer is 5.1 times 10 to the negative 11, oops, that's a 1, meters. So let me go ahead and put that into my spreadsheet. And I can also enter it in for R negative meters because it was the same distance repeated, so I don't need to repeat the calculation. Now my next column says R E positive net. That means, my abbreviation means electric field from the positive, the net electric field from the positive charge. And net means total. So E is KQ over R squared. K, remember, is our constant, 9 times 10 to the 9th. Q, and we're just going to worry about magnitudes because I'm going to show you how to figure out the sign of the charge in a minute, over R squared. (5.1) times 10 to the negative 11 squared. So if I put that in the calculator, I get 5.5 times 10 to the 11th. That's positive 11. And the units for electric field are newtons per coulomb. And if you look back at the formula, you can see where we get that. So let me enter that in my block here. And let's look back at our picture to see what direction that's headed, to see if I need to put a positive or a negative when I change it to components. So back to our picture. Okay, we are now looking at, let me become an arrow here, point A, electric field contribution from the positive charge. We know that electric field goes away from positive and towards negative. So at point A, it's going to go straight this way along the x-axis. So that is the positive direction, so it'll be a positive x component. And since it's only directed horizontally, it will have a 0 y component. So angle to the x-axis is 0. X component is equal to the net electric field because there is no y component. Y component is 0. And then I get over to E negative net. Well, the electric field formula is the same, and all of the numbers in it are the same, so it will also equal the same as E positive net, because the distance is the same. So let's look at how that is oriented on our diagram. Back to our diagram. It'll be a different color arrow this time, it'll be red this time. So now point A, remember, electric field is oriented from positive to negative. So starting at point A, I'm going to go towards the negative. I'm just going to draw a little above so you can see where they're lining up there, rather than right on top of each other so you can't see the previous arrow. And it's pointed directly towards it. It's the same size, so the length of the arrow is the same. These are not drawn to any particular scale, just to show you how they're oriented. And it also is drawn to the right, so that's a positive x component and a 0 y component. So let me go ahead and put that in. Pretty easy when you have them all on the x-axis like this. Oops. I'm going to put that in the wrong column. That is the angle. The angle is 0. This is the x component. Put the wrong button there. Y component is 0. All right, now we're adding the vectors together. Well, the total x component will equal the x component from the positive charge plus the x component from the negative charge right here. Remember that negative indicates the negative charge, not a negative value of the component. The total y component will be total y component of the positive charge, which is 0, plus the total y component of the negative charge, which is also 0. So that answer will be 0. Then, that's my abbreviation for Pythagorean theorem. We will find the total size of the vector by doing Pythagorean theorem, triangle, except in this case it is just a vector in the x direction, not an actual triangle. So it's actually equal to just the x component itself, and the angle to the positive x-axis in this case is 0, because the angle to the positive x-axis for each of those other circumstances was 0. So the vector, total vector at that point, if I use a third color to represent that, will be, let's get right in the middle, let's see, they go back here, will be a vector twice as long, so starting at point A, directed in this direction will be the net electric field from both charges at point A. Pretty easy when you're doing it that way. Well, the next calculation I'm going to do is for point D, where it is not directly in line with the charges, with the main axis that goes through the two charges.